All right, well, hopefully this will go a little bit quicker than last time. It's just an introduction to the idea of Coulomb's law. Before we get into that, we really need to talk about some of the SI prefixes that we'll be seeing over and over again this unit, this chapter, this semester. Going all the way from giga to pico, we'll be using a lot of those throughout the semester, so you need to be familiar with those, know where you can reference them. You can always come back to the beginning of this lecture. But just another quick reminder of what's going on with these lectures. I would strongly recommend opening up your books. We're in chapter 15. If you have any of the last 3 versions of the textbook, it has basically the same material. Nice thing about this class, the physics hasn't changed very much. Some of the applications have changed, and some of the way the book presents the material has changed, but the basic idea is still the same. All right, so if we go back to late 1700s, slightly before the time of the French Revolution, Charles Coulomb was doing experiments with electric charges. He found that opposite charges attract, like charges repel, and he was actually starting to quantify that. And he would perform fairly precise measurements dealing with how these charges would react. So basically what he figured out is that when you had a force, it depended like 1 over the distance between the 2 charges squared. So r we use instead of radius of a sphere, it's kind of from the same same place that if you use the force due to gravity, where you had a g m1 m2 over r squared. That came about because it was first described with the solar system, where r, the distance between the sun and the earth, was also the average of the earth's orbital radius. So we use that same symbol at this point. So the distance r, don't overthink it and divide the distance between the 2 by 2, because radius versus diameter. This is the distance from the center of one object to the center of the other. So the force goes like 1 over that distance squared. So if you go twice as far away, it'll be 1/4 the force. And the direction is always along the same line between one charge to the other. Right? You put two charges along the x-axis, they aren't going to start deflecting along the y-axis. All right, and the force depended not just on on one of the charges, but the product between the 2 charges, Q1 times Q2. And he once again showed that like charges repel, opposite charges attract. All right, this is the first equation of our real equation of the semester, and one that we're going to spend most of Wednesday's class looking into. It's the idea of Coulomb's law. The electric force depends on this symbol K sub E, Q1, Q2 over R squared. So it's a constant, which basically is a conversion factor between newtons, meters, and coulombs. All right, K sub E, that's Coulomb's constant. 8.9875 times 10 to the 9th. We'll just use 9 times 10 to the 9th. It's a lot easier to deal with. I'd like you guys to think about that. What should the units of K sub E be? So we have this constant, coulombs divided by meters squared. All right, so let's plug in. You'll see what the units are, but see if you can figure out why they are that. All right, so let's imagine you have 2 identical 4 microcoulomb charges, so using those SI prefixes again, that are held 3 millimeters apart. So whenever you attack the problem like this, figure out what values you need to do. So I'm just going to use Coulomb's law. I'm going to plug into it. So K, 9 times 10 to the 9th. Then I'm going to do 4 microcoulombs. Micro is 10 to the minus 6. But I have 2 of them, Q1 times Q2, and they're identical, so squared divided by the distance squared. And when I plug that in, I get 16,000 newtons. The number in the front works out for me because The 3 squared gives me 9, and that cancels out the 9 here. So we just have 4 squared, which is 16. So I assume I'm within a few factors of 10 of the correct answer. And you have to figure out, is the force attractive or repulsive? You could always say, well, that's a kind of a repulsive answer, but that doesn't quite get us where we want to go. Okay, a few numbers that you're going to need to know. Just sock them away somewhere you're going to be able to look them up very quickly, is some of the properties of those 3 basic elementary particles that I talked about last time: the electron, the proton, and the neutron. So the charge of the electron is negative, the elementary charge. Proton is positive, neutron is 0. And the mass of the proton and the neutron is pretty much the same within the number of significant figures I included here. And then the mass of the electron is quite a bit smaller, about 1,800 times smaller. Right? This symbol E, sometimes Q sub E, is what's called the elementary charge. It's the charge of the electron or the proton. That's 1.6 times 10 to the minus 19th coulombs. That's one of those numbers you're going to need to get to know. It's just like if you're in chemistry, you get to learn Avogadro's constant pretty easily, but the elementary charge shows up for the rest of this first set of units, set of chapters. All right. Well, that's going to be the end of this other part of tonight's lecture. What I'd like you guys to do is make sure you come to class with a calculator, pen or pencil, something to write with, something to write on, and be ready to kind of delve into this material and get ready to work together to solve these problems. All right, thank you very much. I'll see you on Wednesday.